So we started off this problem and then we ran out of time. So number 10, at an accident scene on a level road, investigators measure a car, right? A car's skid mark to be 88 meters long, right? It was a rainy day and the coefficient of friction was estimated to be 0.42. Use these data to determine the speed of the car when the driver slammed and locked on the brakes. Why this car's mass does not matter. Well, first, when we were looking at the car here, this is the displacement vector, and here the wheels. Now, if there are some forces involved, here's the force here, which is Fg, which is the obvious force, is the weight of the car. And then we have F normal going the opposite way. And there's one other force. That force is the frictional force acting in the opposite direction of motion. Now, we all know F friction is equal to mu times the F normal. But in our case right here, F normal, right, is equal to Fg, which is equal to m times g in our case, because it's on a flat, level road, right? So here, my frictional force then is equal to mu times mg. But it is going in the opposite direction, right? It's pointing in the opposite direction. Therefore, we have to use this work kinetic energy equation. Right? Work is only done by the friction here. So work done by friction is equal to kinetic energy final minus the kinetic energy initial. Work, we just said, done by friction is equal to F friction dot delta x. Right? And that is equal to 1/2 mv final squared minus 1/2 mv initial squared. And we also agreed that friction is equal to mu times mg times delta x. And since the angle between the delta x and friction is opposite directions, they are 180 degrees from one another. So you have to multiply that by cosine of 180. That is equal to, what is the final velocity of the car when it comes to rest? Good, like you said, nothing, 0. Right, all right. What's your A game today? Good. Minus 1/2 times mv initial squared. Now, if you take a look at it carefully, the masses cancel out right here. And cosine of 180 is equal to -1, right? So this is -1. So this negative and this negative will cancel out. Okay? So here, mu, m's canceled, mu g delta x is equal to 1/2 vi squared. We're looking for vi, right? So my vi is equal to square root of 2 times mu g delta x. So let's plug it in and find out what's going on. So square root of 2 times mu, which is 0.42, times 9.8 times 88 meters. So if we work it out, here, go 2 times 0.42 times 9.8 times 88. And we have to square root that. So I got something around 26.9 meters per second. I mean, that feels like not that much, But if you were to think about that, right? Um, multiply that by 3.6, and then divide that by 1.61. That's about 60 miles per hour, right? That's about 60 miles per hour. So it's going a little fast for the weather. Right? All right, now comes the last problem. This one was a little bit tricky, okay? Now you have to understand there are two cars involved, right? So here, one car has twice the mass of the second car, all right? So here's car one, and here's car two. Car one has mass, right? I'm going to say mass naught. Car two has twice the mass of car one. Okay, so I could say mass two is equal to twice the mass of car one. And mass one is equal to just ml, right? But only half as much kinetic energy. That means the kinetic energy one is equal to 1/2 mov v1 squared. Right? And this is initial. And kinetic energy 2 initial is equal to, right, half as much. So half of 1/2 MOV1 initial squared. So this is important, right? Understanding this. Now, when both cars are increased by 5 meters per second, okay, then they have same kinetic energies. So kinetic energy final is equal to 1/2 MO times V1 initial plus 5 quantity squared, right, is equal to right? Well, I guess this is, you could say that this one is equal to, right, 1/2 K2 final is equal to, right, 1/2 2MO times, right, V2 final, no, V2 initial, right, V2 initial plus 5 quantity squared. Now this up here is same thing as saying 1/2 2MO times V1 initial, no, V2 initial squared. Because this is what the kinetic energy of this is. But that is equal to half of the original first car's kinetic energy. Now we have everything all pretty much set up. Okay? So we need to find out what this V2 initial is, right, in terms of V1. So we can utilize that to plug it in here to pretty much figure out what the initial velocity of the car 1 is. Okay? So I'm going to need more room. I'm sorry I only gave you this much room. This is horrible. I should have given you more room than this. Let me see if I can find the blank sheet. So if we can, right, figure out what's going on, let's take a look at this equation right here. We'll take a look at this. And then take a look at this and let's solve, right, in terms of V2 initial, in terms of V1 initial. So here, 1/2, right, 1/2 of, right, 1/2 MO V1 initial squared, right, must equal to 1/2 of 2MO times V2 initial squared. So I'm going to cancel out the 1/2s first, like that, okay? And then, if I cancel out the MOs, I can do that. If I divide both sides by 2, on this side, I get 1/4 V1 initial squared, right, is equal to V2 initial squared. If I square root both sides, here I get 1/2 V1 initial is equal to V2 initial. So this is important because I can use this information to plug in here for my V2 initial as 1/2 V1 initial. Then we can eliminate a lot of things. So once we go up speed of 5 meters per second for both cars, the kinetic energies are equal. So I can say now, if we look at this, the green, and then, right, so they say kinetic energy 1 final is equal to kinetic energy 2 final, right? Because if you go up 5 more meters per second for both cars, it's going to happen that way. So 1/2 MO times V1 initial plus 5 quantity squared is equal to 1/2 times 2MO times V2 initial plus 5 squared. But we're going to substitute this V2 initial with 1/2 V1 in here. Okay? So, let's see. I'm going to again cancel out the 1/2 MO with 1/2 MO here. On this side, curses, foiled again. We have to foil this, right? So we have V1 initial squared plus 10V1 initial plus 25 on this side is equal to, on this side, I have 2 times. Remember, this is V2 initial, which is the same thing as saying 1/2 V1 initial plus 5 quantity squared. That means I can actually foil this as well. So here we have V1 initial squared plus 10V1 initial plus 25 is equal to 2 times. Here I have 1/2 V1 initial times 5 is 2.5, right? So, well, let's do 1/4 V1 initial squared plus 2.5 times 2 is 5, right? Times that by, and then plus 5 squared, which is 25. Okay? So let's distribute this 2 through. In that case, I have 1/2 V1 initial squared plus 10 V1 initial plus 50. That is equal to V1 initial squared plus 10 V1 initial plus 25. Okay? All right. Well, you can look at this. This 10 V1 here initial and this 10 V1 initials here. So we can probably cancel those out. Right? And then let's consolidate these. If I bring this to this side, I get positive 1/2 V1 initial squared. Because 1 minus half is half, positive half, right? This here, if I bring this to the other side, I get 25 on the other side. Multiply this by 2 on both sides, I get my V1 initial squared is equal to 50. So my V1 initial is equal to square root of 50, which is 7.07 meters per second. Therefore, going back up to this, since I know that V2 initial is equal to 1/2 V1 initial, now I can say 1/2 of 7.07 is my V2 initial. So my V2 initial is equal to 3.54 meters per second. Whew. That was a workout and a half, actually. I mean, it was a lot of algebraic manipulations, but it was still possible. So it was not a trivial problem. It was a pretty challenging problem. All right. So that's how fast they were going initially before they added 5 meters per second to both cars. All right. All righty then. Let's move on. I'll put this up on Schoology. I'll put it like this. So I'll put this page and I'll put this page afterwards. So you guys have it. Okay. Now let's take a look at lesson 3. Potential energy. Understanding potential energy. History of science. Enrique Joule's experiment. What happens as mass drops? Well, I don't know if his name is Enrique, actually. You gotta fact check me on that, right? Jules, his father was actually a brewer. I'm talking about like beer. So his father owned a brewery, and when he was young, he noticed when his father's workers actually stirred a big vat of like barley and malt and hops, the temperature of the whole vat used to rise up. So he figured there must be some relationship between mechanical energy put into a system and rise in temperature. So the thermal energy and mechanical energy has to be related. So he made this device right here, right, that he wound up this string and raised this weight up to a certain height. And then when he let that drop, the dropping of this weight would cause this spindle to spin transferring mechanical energy into the system here of the liquid, stirring this thing up to cause this temperature to rise. And he measured that. So he measured this potential energy of this weight transferring into kinetic energy that transferred into thermal energy afterwards. And he got his name in the Physics and Scientific History Hall of Fame forever. Okay? So, let's understand what potential energy is. Potential energy is energy of location. You have to think of it that way. Okay? So potential energy is energy of location, location, location. Otherwise known as just PE, is energy of location. Okay? And the location usually means height. Okay? The change in height will actually change the potential energy. Okay? So if you think about like riding a roller coaster, okay, on the way up, on the, click, 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 on the way up the roller coaster ride, like, click, 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 it's going up, right? You're gaining potential energy because you are doing work against the gravity to raise that mass up a certain height. Okay? So here, you're fighting against gravity, basically, or you're doing work against the gravity going up this way. So the work that you have to do is minimum of same amount of Fg here, right? Going up this way, so mg delta y times cosine of 180 is how much work is done by gravity, which is negative work. Because Fg is down, delta y is up, so angle between that is 180 degrees. So work done by gravity on whatever you are raising is doing negative work. Okay. Now on the way down, your Fg and your delta y is in the same direction. So as mass falls from the height, what is work done? Well, work done by gravity on the way down is Fg dot delta y, but this time Fg and delta y are in the same direction, so we say cosine of 0 degrees. Therefore, it's positive mg times y final minus the y initial. Okay, so your gravity is doing positive work when it's on the way down, negative work on the way up. Okay, so you could write that down. So gravity does negative work on the way up, and gravity does positive work on the way down. Okay? So as you lift the mass against the gravity, picture a roller coaster, click, 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 right? Very tall first hill. The motion, delta y, and the roller coaster is against the force of gravity, so the gravity does negative work. Right? Gravitational potential energy being stored is the following. So the change in potential energy is equal to negative of work done by gravity. So on the way up, since potential energy, change in potential energy is negative of negative mg delta y, you'll get positive mg delta y. So this is very important. So change in potential energy is positive mg y final minus y initial. Then, as the roller coaster reaches top of the hill, all the potential energy is unloaded, right? The force of gravity does positive work, and the force and displacement vector is in line. And the roller coaster flies down the hill, converting all the potential energy into heart in your throat kinetic energy. All right? So that potential energy transfers to kinetic energy. Right? So potential energy transferred to kinetic energy. So as the potential energy decreases, kinetic energy increases. Right? And if you go up to next hill, the kinetic energy decreases and potential energy increases. And so they're really feeding each other. All right? So what's the mathematical potential energy function as gravity then? Well, they usually use U as potential energy. Right? So potential energy can also be represented as U. And U can be used as a function of Y, position in the Y direction. Okay? So this is a potential energy function for gravity. So this is known as gravitational potential energy. All right? Gravitational potential energy. So you could say potential energy sub G is equal to mg y, or simply mgh for height. Okay? So if you were to think about graphing the potential energy of gravity as a function of position, right? I guess you could say this should be y, not x. Then potential energy function versus y should be very linear because why? First of all, my y-intercept is 0, so here it starts at the origin. M and g are constants. So this is the slope, and the slope itself is mg. Okay, slope itself is mg. So potential energy of gravitation is just simply mgy. Now we could have potential energy gravitation at any location, right? But where do you set your zero? Do you set your zero at the floor of 281? Or do you set your zero at the floor of the first floor? Or you could set your floor to be at the top of the roof if you want to. That's all depends on you, how you want it. Okay? You don't always have to start from the basement all the time. That's why it's very important to understand it has to be change in potential energy. How much change is there, right, given height where you want to set your zero. So it's always going to be relative to some reference point of zero that you set. Okay? So if there's no friction involved, if there's no work done by friction, then total mechanical energy initial, right, must be equal to the total mechanical energy final. Okay, so remember when we talked about like how work is equal to change in kinetic energy? Well, now this work can also equal to not just kinetic energy, but also change in potential energy gravitation. And usually this work is done by friction or some applied force or some other, right? This work, if the work done by friction is zero, right? If this is zero, right? Then zero is equal to kinetic energy final minus the kinetic energy initial plus potential energy gravitation final minus the potential energy gravitation initial. If I bring the negative kinetic energy initial and negative potential energy gravitation initial to the other side of the equal sign, they become positive. So kinetic energy initial plus the potential energy gravitation initial is equal to kinetic energy final minus the potential energy gravitation final. Plus. These become pluses on the other side. So what does that mean? That means this is just total initial mechanical energy. So total energy initial must equal to, this is total mechanical energy final. So must equal to total mechanical energy final. This is conservation of energy. The energy is conserved. Total energy that you start with initially must equal to total energy final you end up with. This is only true again if there's no friction in the problem, when the work done by friction is zero. Okay? So total energy that you start with, kinetic energy plus potential energy, at any point in any time has to be equal to each other, no matter where you are comparing. Okay? No matter where you are comparing, they have to equal to each other. So let's take a look at an example problem here. We have 1 kilogram mass and it's dropped. As soon as you hear the word dropped, you know the initial velocity is zero, right? As soon as you hear the word dropped. So it has height of 20 meters. This is y initial. For each of the height below, find the kinetic energy, potential energy, and total mechanical energy. The ME means total mechanical energy. Right? So initially, right here, at this point, so I'm going to say point A, point B, point C, and point D. I'm not going to put any initial, final at all. I'm just going to put point A, point B, point C. Initially, I have to ask these questions. Kinetic energy plus potential energy gravitation. At point A, is it moving? No. Why not? Because it is dropped, so it is not moving. Does it have height compared to the ground right here? Yes, I do have height. So this is total mechanical energy, right? Therefore, I have 0 plus mgy at A. that is equal to, right, 0 plus 1 times 9.8 times 20. So what is that equal to? 196? 196 joules. All right? Now, when I see this, this is the total mechanical energy. Right? Total mechanical energy. So no matter where you are during this path, whether it's point B, point C, or point D, total energy has to always add up to this, 196, right? So at this point, total energy at B is 196 joules. Total energy at C is 196 joules. Total energy at D is 196 joules. Well, here I have, again, kinetic energy plus potential energy, gravitation. Is it moving at point B? Yeah, it's definitely moving. So I have kinetic energy. So I definitely have kinetic energy at point B. Does it have height at point B? And the answer is yes. So I have potential energy. I have both. Well, when I add these two energies up, that has to equal to total energy at B. We already know how much total energy we have already, and that is 196 joules. We don't know exactly how much kinetic energy we have at B, but we could figure it out. But here, I know my potential energy, gravitation at B is mgyb. What is mgyb? That is 1 times 9.8 times height at B is 13. So potential energy at point B is 127.4 joules. Therefore, my kinetic energy at point B is equal to, right, 196 minus that potential energy, and I get 68.6 joules. That's how much kinetic energy I have at point B. What about at point C? At point C, right, again, kinetic energy at C plus potential energy, gravitation at C must equal to total energy at point C. We already know exactly how much total energy we have at point C, and that is 196. That has to equal to kinetic energy at C plus potential energy, gravitation at C is mgyc. So kinetic energy at C plus 1 times 9.8 times 7, right? YC is 7, is equal to 196. So what is 9.8 times 7? I see that as 68.6. So kinetic energy at C plus 68.6 is equal to 196. So kinetic energy at C is equal to 127.4 joules. Now, once we know how much kinetic energy we have, we can figure out how fast it goes at that point as well. Because you could set that kinetic energy equal to 1 half mv squared. Does that make sense? Right? Because we can say that this is also equal to 1 half mv at b squared. And we could set that equal to, right, 1 half mv at c squared. So we could actually calculate how fast it's moving at those points. And at D, kinetic energy at D plus potential energy at D, right, is equal to total energy at D. We already know total energy at D is 196. How much potential energy do I have at point D? None, because the height is 0. You know this is 0. So total kinetic energy is just all potential energy. I mean, kinetic energy at D is total energy at D. So kinetic energy at D is 196 because my potential energy at D is 0. All right. All right. So, any questions at home? No? Okay. All right. Then I'm going to give you guys a breakout session and I'll let you do some homework together. All right. Let's see. Okay. Let's see if I could give you maybe like 25 minutes to work on this. So let me see if you can work on page 19 and 20 and page 21. They look like they're a lot, but there's only 5 problems. So I'll give you about 25 minutes, 5 minutes for each problem, and I'm going to set you guys on a breakout session. All right? And we'll meet back at, I guess, 25 minutes later, which is around 42-ish. Okay? All right? So I'll pause this. All right, so here, Jane is looking for Tarzan. He's in trouble now. You know, when Jane's looking for Tarzan, what do? If you're a Tarzan, you just apologize. No matter what, you just say, I'm sorry. You start with that first, right? Oh boy. So, when Jane is looking for Tarzan and she's running at top speed, that means she's very angry. Okay? So you start with apology. Whatever I did, I'm sorry. Or whatever I didn't do, I'm really, really sorry. So here, Jane running at top speed to look for Tarzan. We'll give her red hair. And she's running with initial velocity or initial speed of 5.6 meters per second. Then she grabs on the vine. So this is the initial condition. And she grabs on the vine and then she swings upwards. Okay. And when she swings upwards, right, her motion stops at the top of the swing. So at final condition, her final velocity is instantaneously 0 at the top of the swing. But she does gain height. Right? So here's her y final, which is the height that she's going to gain. And here's the y initial. We're going to consider y initial to be 0. Now notice, like, we're going through her belly button because that's the center of mass of her, right? So we're going to consider her as a particle where all her mass is concentrated at the belly button, okay? So we know that when this happens, the total energy initial must equal to total energy final, okay? Total energy initial, well, kinetic energy initial plus the potential energy gravitation initial must equal to kinetic energy final plus potential energy gravitation final. Initially, is she moving? And the answer is yes, so kinetic energy stays. Does she have any height initially? No. So, no potential energy initial. At final, is she moving? No. So, no kinetic energy final. Does she gain any height? And the answer is yes. So, that remains. So, here, kinetic energy initial is 1/2 mv initial squared. That has to equal to mgy final. Look what happens to her mass. We don't have to find out how much she weighs. That's good for her, right? She doesn't want to give that out. Therefore, we can find out exactly how high she gets. Well, not that kind of way, but you know what I mean, right? How much height she gains, right? I'm sorry. Sorry for my language there. So 1/2 times, right? 5.6 squared is equal to 9.8 h, because height final is just h. So if we solve for h correctly, she only goes up 1.6 meters. That's not that high, right? 1.6 meters is about the height of a human being. Okay. Maybe Tarzan is not that much in trouble. I don't know. Well, what about part B? Does the length of vine affect your answer? What do you say? Well, what if the length of vine is only like a meter? What would happen to her? If the length of vine is a meter, if she's going to reach up to 1.6, she's going to go up way over and then like come back down, right? What if the length of vine is less than 0.8 meters? What would happen then? She's gonna go up, she's gonna go up, and then she's gonna go. Yeah, then she'll be very angry at Tarzan because she'll blame it on Tarzan, right? So why couldn't you get a bigger vine, right? So length of vine does matter if it's anything less than, you know, if it's short. That's why I think they said, from a tall tree. So they made the vine really long to make sure that, she doesn't fall down. All right. So the answer to that is yes, right? Length of vine does matter, right? If it's less than zero point 0.8 meters and she's going to go around the limb of the vine that's hanging, so she's going to be going in circles then, okay? So I would make sure the vine is long enough so she doesn't get hurt. All right, next. A novice skier, right, starting from rest, slides down a frictionless, there's no friction for this because it's all very icy. It's probably Poconos. Poconos is always icy, right? So frictionless 25-degree incline whose vertical height So here, y initial is 125 meters and y final is equal to 0. And the skier starts from rest, right? So skier starts from rest and skis down. So initial velocity is 0. So at, at the bottom of the slope, the skier must be going pretty darn fast, right? Because there's no work done by friction, okay? So this is the initial and this is the final. So total energy initial must equal to total energy final. Kinetic energy initial plus potential energy gravitation initial. Oh, we'll finish this next time. We'll finish this on Thursday. All right. Have a wonderful day, everybody. All right.